today's lecture, let me at first introduce myself. So my name is Himanshu Sekhar, and I'm currently an MTech student of IIT Guwahati. I'm been hired as a data scientist at Legato Health Technologies, which is a subsidiary company of Anthem, which is a Fortune 29 company. I've cracked GATE 3 times, subsequently in 2017, 18, and 2019. So yeah, and before moving to the just lecture, I just want to make 2 points. The first one is like the subjects which I am going to teach you at IGC, the programming language, and plus the data structures, plus the algorithms. So these three subjects are not only important from the GATE perspective, but they are also very much important if you are just looking for placement from any of these IITs. So most of the yeah. So most of the students which just want to just appear in this GATE examination is because they want to get into IITs or NITs, and they just want a good placement. So these three subjects are very much important, not only for this from this GATE point of view, but also for this placement point of view. Okay, so yeah, this is the first point, and the second point is that is regarding the slides which I have just prepared. So you might see that the in the subsequent slide that each of these slide I have divided into two sections, the rough section, and the second is the fair section. Okay, so this fair section I have just included so that you can just take notes pretty much easily, so that you just don't miss any point. Okay, and this rough section is there because I'm not interested in just only slide reading. Okay, so I just don't like this idea of slide reading where I am just the text is written over the screen, I'm just reading these slides, and this is not a good form of teaching. So what I am more interested is in interactive teaching. Okay, so interactive teaching is what I like. So what I would do in the subsequent slide, I would just in this rough part, I would just write the concepts on this screen, and I would teach the concept, and this fair part you can just use for this note making. Okay, so yeah, so let me clear the screen. Okay, so yeah, so starting with the agenda of today's lecture is to introduce you to the time complexity. Okay, so I would cover this time complexity topic very briefly. Okay, I'll give you a very brief introduction, and then we just move to the this topic array. Okay, so the main focus is array, only array data structure, but to learn this the array in this array there are various algorithms which are present. Okay, so various algorithms which are there which are performed on this the array data structure. So for these algorithms, I would also be just specifying the time complexity of different algorithms. So that's why a brief introduction of array is pretty much important. Okay, so this is the agenda of this lecture. So let me quickly just start with this array with this time complexity. Okay. Okay. So most of you or some of you might be aware of this concept of time complexity. Okay. So time complexity is the time measured in the terms of number of steps or the operations, okay, involved. Okay. So yeah, so let me write it again very quickly. So I was teaching you this time complexity concept. So time complexity is nothing but the time or in the terms of number of steps taken by some algorithm. Okay, to perform yeah, to perform some task. Okay, so basically, let's say let's take a time an algorithm. Let's say A1. So suppose the job of this algorithm A1 is to sort. Okay, to perform sorting sorting the numbers. Okay, the task of this A1. So it would just require some steps. Okay, so algorithm is nothing but a sequence of steps. Okay, sequence of steps is an algorithm which is used to perform some task, and the task here is to just sort. Okay, sort the numbers which are given to it. Okay, so the number of steps. Okay, we if we just count the number of steps only for this algorithm, so it would just give me the time complexity. Okay, so basically we are not talking about time in milliseconds, okay, or seconds. So we are not very much interested. So this is a very important note, that this time we are not interested in second or millisecond or nanosecond. So this time we just don't want. Okay, we just focus on time in number of steps. Okay, and I would tell you why. So any algorithm, let's suppose A1, we just take this algorithm A1. So this algorithm A1, if I run on some system or CPU one, and let's just run this algorithm on two different CPUs, CPU one and CPU two. So both the performance on of this algorithm on this CPU one and CPU two would very much depend on this performance of these both of these CPUs also. So what is the clock cycle of these CPUs, and the different parameters of these CPUs would determine the time which is taken in seconds, milliseconds, and nanoseconds. But we are here to just find the performance of algorithm and not the CPU. So that's why what we do, we don't compare, we just don't take care about the time in the terms of second, milliseconds, or nanosecond. What we do, we just compare, we just find out the number of steps which is just number of steps which is involved in some any algorithm. So the A1, the number of steps which A1 would be using, or the number of steps which the A1 would be performing to perform some task. So the both would be similar. That would be similar for both the CPUs. Okay, so that's why this time complexity. If I talk about this time complexity, you should be clear about the thing that we are just taking into consideration the number of steps and not the time in seconds and milliseconds. Yeah, so this is about the introduction of time complexity. So it would be more clear if I take one example. So let me just write a loop. I equals 0, I is less than n, and I plus plus. And what I'm doing, I'm just printing this I. Okay, so yeah, so you might be aware of this kind of syntax. So this is a very simple for loop. Okay, and yeah, so this part, this very part is the initialization of the variable I with the value 0. This is the comparison part, this is the increment part, and this is the body. Okay, this is the body of the loop. Okay, so we are here to count the number of steps which is involved. Okay, so we just want to know what is the number of steps which is involved in this algorithm, or a simple for loop. Okay, so if you look at it carefully, you'll just find it out. Let me just change the color. Okay, so yeah, so if you look at it carefully, you'll find it out that this initialization part, okay, this I equals 0 part would only happen one time. Okay, for any loop this initialization would only happen for one time. Okay, and we need to just also find out how many times these other statements just happen or get executed. So before just looking at the number of times these statements are executed, let me at first just write the output of this loop. Okay, so the output of this loop would be, first the I value is 0. So with this I value 0, it would just come into the loop based on this condition, I is less than n. So let's take n to be 10. Okay, so this condition would be true, and I would come, the loop would come to its body, and the I would be printed. So 0 would be printed. Again, the value of I would be incremented. So and again this condition would be true. So 1 would be printed, as similarly it would get printed to 9, because I, for I less than the value of I to be less than n or 10, this condition would be true, and this part would be executed. Okay, so this would be the output of this for loop. So now so now just consider this comparison operator, and let's check how many times this comparison operator just gets executed. So if you look at this comparison operator carefully, you'll find out for I, the value of I to be from 0, 1 up to n. Okay, so this comparison operator I is less than n would be true. Okay, and for this value I equals 10, this comparison operator I is less than n would be false. Okay, and for all these values, this comparison operator would be performed or executed. So this comparison operator would be executed for n plus 1 times. Okay, so it would be the value of the I would be checked for n times to be true. Okay, and for these n times, for which the value is true, it would just enter the body part, and it would just execute the body. And for this, the rest one part, for the rest one value of I to be equal to 10, this comparison operator would return false, and it would just state that the execution of this for loop is over, and the program control should reach out of the for loop, which is here. Okay, so if after this false part is there, so the execution would go to the next statements which are there after the for loop. Okay, so this implies that this comparison operator works for, or gets executed for, n plus 1 times. Okay, now talking about this I plus plus, you'll see that the value of I is incremented from 0 to 1, then 1 to 2, and again 8 to 9. So it, if you look at it carefully, it would just run for n times. Okay, so n times the value would be incremented, and yeah, uh, so one statement is left, which is this print. And yeah, let me just tell you this, that this is a pseudo code. You just don't go for the syntax. So it is very much similar to C or C++ code, but this print statement is not there. So printf is there in C, and cout is there in C++. So you don't need to be confused. So I'll be using pseudo codes mostly in this course. Okay, so yeah, so just then talking about this body, about this body part. So this print statement would be executed for the values of I, such that for the values of I such that this comparison operator is true, and this comparison operator is true for n times. Okay, and for those n times, it would just enter this body part, and this statement would be executed. Okay, so these are all the, we have checked for all the number of steps. Okay, and for yeah, so for how many times all these statements are just getting executed, we have checked. So let me write the number of steps over here. So it would be 1 for initialization, n plus 1 the execution would happen for this comparison operator, and n for this increment operator, and for this print statement this is n. Okay, so if I count, so there would be 3 n's. Okay, 3n and plus 2. Okay. Okay, so these are the number of steps, okay, which are yeah, so these are the total number of steps which are involved in execution of this for loop. So, and we have also seen that the time complexity equals number of steps. Okay, in the definition only we have seen that the time complexity is number of steps. So the question arises that is time complexity of this loop 3n plus 2? So this is the question now. Okay, so is the time complexity of this is 3n plus 2, because the steps we have found, and by the definition time complexity is number of steps. So is time complexity 3n plus 2? So this is the question which arises now. Okay, so as I have already told you, so whatever I would be discussing on that rough, it would be written over here in the next slide in a fair manner, so that you could just take the notes. So time complexity definition is the number of operations or the steps required by the algorithm to solve the problem. I've taken a similar for loop where I've started the value from 0, I equal to 0, but it is pretty much similar. So this the total number of steps can be calculated by this thing over here. So one step is for this initialization. This is taking one step, n plus 1 for comparison operator, this comparison operator, and n for increment, this one, and yeah, n for this body part. Okay, so yeah, so the total number of steps is 3n plus 2. So the question arises is this the time complexity? Okay, so we'll just move to this question. Okay, so before answering the question, let me just introduce you to one more concept. Okay, so yeah, so one more concept which is important to answer that question is this asymptotic notation. Okay, so asymptotic notation is nothing but the representation of time complexity of algorithms. Okay, this is the first thing, and asymptotic notation is also used to compare different algorithms. So this point is pretty much understandable. Okay, like this is the representation of time complexity. Okay, so we can easily represent the time complexity of any algorithm using asymptotic notation. But what do I mean with this? Like how can I just use this to compare different algorithms? So let me take an example again to explain this. So consider this algorithm A1 and this algorithm A2. Both these algorithms are just meant for this sorting. Okay, I am again going for this sorting problem. So let's see, both of these algorithms A1 and A2 are just designed or implemented for this sorting, for performing sorting of numbers. Okay, so A1 would be having some time complexity TC1, and A2 similarly would be having some time complexity TC2. Okay, so TC1 we can represent using asymptotic notation one, say, because we are according to the definition we can represent the time complexity of any algorithm using its asymptotic notation. Similarly, for TC2, representing TC2, we could have just asymptotic notation of this second algorithm. So when we have arrived at their asymptotic notation, we could just simply compare. Okay, we could just easily compare the asymptotic notations, and for just determining which sorting algorithm is better than other. Okay, so this is the main the use case of this asymptotic notation, that we need to we can just represent the time complexity, and we can also compare the different algorithms. Okay, So there are basically 5 types of asymptotic notations which are there, and out of which we would be learning 3 types over here only, learning briefly only, and the remaining 2 types would be discussed in the algorithm subject, and these are pretty much similar to these 3 types which we are going to study here, and these 3 types would also be explained deeply when we just enter the algorithm subject. Okay, so let me just quickly give an overview of these 3 types of asymptotic notation. The first one is the big O, okay, which is represented by a capital O. The second one is omega. So this is the representation omega. And the third one is theta. Okay, so this is the representation. Okay, so yeah. So what big O is used to, big O is basically used to represent the upper bound. Okay, so if you don't know about this upper bound thing, so bear with me, I'll just explain what this bound thing is, what is this upper bound. So please, just for the time being, bear with me, and just remember that this big O is used for just representing the upper bound. The omega is used to represent the lower bound and upper bound of time only. Okay, similarly this is for lower bound of time, and this theta is for exact bound of time. Okay, so yeah. So, so for that understanding the three bound of time, so let me just take this, take this. So, what is this bound of time? So, consider some algorithm A1, let's suppose, and so basically, if you see the for most of the algorithms, it would be like the performance would depend upon input. Okay. So suppose some algorithm A1 is there. So it would just perform differently for different inputs. Okay. So this is the case with most of the algorithms. Okay. So many algorithms, this case is there, that for the performance of this algorithm, sorry, the performance of this algorithm would depend upon the input. Okay. So for some input, let's suppose input 1, what it would just have the, it can have the best performance. Okay, and for some let's suppose input 2, it can have the worst performance. Okay, so if the performance is best, it means that it is in terms of time. If I just want to just make a statement, it would be least time taken, because we always want that the algorithm which we have should take the least time, and that's the best performance. Okay, and for this worst performance, the time would be the largest. Okay, the largest time. Okay, so this least time is nothing but the lower bound. Okay, so this is the lower bound, and this largest time is the upper bound of time. Okay, so so this thing I would also like to just for this I would also like to give one another example so that it is a bit more clear. So you might have heard about this algorithm quickshot. So there is a pretty much interesting characteristic of this quickshot is that if you just give the input to be ascending or descending, the performance is going to be worst. Okay, so it would just perform worstly if you just give the input in ascending or descending order. And if the performance is worst, what is the time? The time is the most or the largest time. Okay, and this is a case of what? The upper bound of time. Okay, because yeah, because so yeah, so if again if it is not clear, so suppose the algorithm quick shot is this is the worst performance. Okay, so this is worst performance in terms of time. Okay, so if I'm representing this line to be the time, and the performance, the time which is taken by the quick shot. So suppose this is the worst performance which it is, the quick shot is having for these kind of inputs, ascending and descending order. So any for any other input which is not ascending or descending, the performance, or the performance would be better, and the time would be less than only. Okay, for from this point of view. Okay, any input would take less time than this time which is taken by this input, ascending and descending. Okay, so that's why it is called upper bound. Okay, so you should be just very much comfortable with this concept, because this is very important concept, and this you would need to understand very, yeah, very much, so that you can just understand the time complexity of different algorithms. So that's why I'm putting that much stress. So this that's why this is called the upper bound of time, and this, for some input, the performance would be best, and any for any input the time taken would be greater than only, greater than or equal to only. Okay, this, so that's why this is called the lower bound. Okay, so I hope you must be now comfortable with this big O, and yeah, and yeah, so for this upper bound, we would be using this big O notation for representation, and this, for this lower bound, we would be using this omega. And this would be clear when we just take some more examples, but the concept should be clear, I just hope. And for this theta, it is used to just represent the exact bound. Okay, so you might this would also be clear with some example, but let me just give you a small example, so that you could just have the glimpse of this concept. Okay, so for there are some algorithms. Okay, there are some algorithms which would not depend on, okay, not depend on input. Okay, so what I mean, they are not depending on input, so they would be exactly running that much time. Okay, so if there is a loop, okay, that should be executed for n times, so there should be no case in this loop which could break the loop in between. Okay, so it would, if it has to just execute n times, it would be executing for n times. And this is what this thing is, the exact bound. It is taking n times for all input for all the times. So yeah, and this is the exact bound. And yeah, it would soon be clear. If it's not clear now, we'll just, in the next example only, we'll be just seeing this. Okay, and yeah, so this is about big O, which is the upper bound, big omega, which is the lower bound, and theta, which is the exact bound. Let me just wipe it out. Okay, yeah. So yeah, we have what we have seen is, we have seen the asymptotic notation also, and for the previous loop we have found that the number of steps, if you could remember, it was 3n plus 2 after all the initialization, considering all the initialization, comparison, and everything. It was 3n plus 2. Okay, so yeah, and we have seen that to represent this time complexity, we need to use asymptotic notation only. Okay, and one more note I'm just have to make, which is very important, that in asymptotic notation, I would write asymptotic notation as an, we ignore constants and coefficients. Okay, so yeah, in coefficient in sorry in asymptotic notation, what we do, we just need to ignore constant and coefficients. So 1 second. Yeah, so yeah, so if you look at this part, this number of steps thing, so what is constant? This 2 is constant. Okay, so we need to just ignore this 2. And for coefficient, this is the coefficient, so we need to just ignore this also. So I after ignoring these two things, I'll call this I generally call this the step part of the time complexity, and the step part of time complexity is n. Okay, so which is left, after considering this note that we are ignoring constants and coefficients. So there is a very much there is a reason behind this why we are ignoring these constant and coefficients. So you don't need to just bother about it now. We'll just discuss it minutely when we'll just start the algorithm subject. Okay, so but till now this is for this lecture or for data structure subject, it is yeah, it is enough that you know that we just ignore constant and coefficients. Okay, so this is the step part. So this is the first achievement which we would use for this writing down the asymptotic notation. The second thing which we this is the first thing which we use. Okay, and the second thing is we need to determine. Okay, we need to determine whether we have to use a big O, whether we have to use this omega, and whether we have to use this theta. And this step part we would just include in this parenthesis. Okay, so whatever we consider, okay, we just reach to a conclusion that which notation should be used. We would just write the step part inside the parenthesis, and it would just complete the asymptotic notation. Okay, so for determining which representation should be used, let me just write down the loop again. I equals 0, I is less than n, I plus plus, and we are printing I. Okay. So yeah, so if you look at this loop very carefully, you'll find out the value of I is going to be from 0 to n. So whatever this situation is, this would happen. Okay, there is no certain case in this for loop which would just let the loop execution to end in between. Okay, there is no such condition in this loop. So it would run exactly n times. Okay, so if you you might have figured right now that for the exact kind of thing, for the for just showing the exact, representing the exact bound. Okay, we just use what? We just use this theta notation. Okay, so theta notation would be used, and this is the step part which would come inside the parenthesis. So theta of n would be the time complexity of this loop. Okay, so this is how we determine the time complexity or asymptotic notation of any algorithm out there. Okay, so this is the only basic way. Okay, so let me wipe it out. So yeah, so asymptotic notation, it is used, I have already told you, in order to compare the rate of growth of two algorithms. So rate of growth of two algorithms is nothing but the time complexity, and I'll tell you why. So basically, when we are just there is one another concept in this time complexity, that when we just consider this time complexity, we just we are just focusing on how the algorithm is going to perform for high n. Okay, where n is the n, yeah, n is the input. Okay, so when n tends to, n tends to infinity, or the high number of n, so what is the performance of algorithm? We just need to determine, and that's only the time complexity. We are not bothered about small number of inputs, we are just bothered about high number of inputs. Okay, and this is the rate of growth, and we can just compare the two algorithms with respect to time and space. And yes, space complexity can also be used, can also be represented using this asymptotic notation. We don't need it right now. Whenever it is needed, I would just explain it to you. And yeah, so for the for just comparing the two algorithms, time wise or space wise, we use asymptotic notation. Big O we use for upper bound, omega for lower bound, and theta for exact bound. This note I have already discussed, that we ignore the constants and coefficients. Time complexity of the previous question I have already told you how it is theta of n. Okay. So this is about basic introduction of time complexity and asymptotic notation, representation of yeah, the representation of time complexity. So let me just move to this uh, array section. Okay, let me change the color. Okay, so yeah, so I'll start with the array topic. Okay, so array is let me first give you the definition of array. Okay, so array is a linear data structure which is used to store homogeneous elements. Okay, so there are two important points which you need to just focus over here. So the first one is this linear data structure part. So what is a linear data structure? And the second one is this homogeneous elements. Okay, so I'll talk about both of these things, so that you are more comfortable with this topic. So the first one is this linear data structure part. Let me write down. Okay. So yeah, so linear data structure means that the elements are are, stored or assessed in sequential manner. Okay, so if you have seen array, the structure of array somewhere, it looks something like this. There is a big chunk and of memory, and there would be small divisions, and the elements which are stored would be two, let's suppose 3 2 1, anything 5 4. Okay, so these are the elements which are stored currently in the array. So yeah, so if you just look at the elements which are stored over here, you will just find a sequence of arrangement. Okay, or a storage, or say assessment or arrangement. Okay, so all of the things would be in a sequential manner. So there is a particular sequence of arrangement, like 3 is coming before 2, 2 is coming before 1, and sequentially. Okay, so due to this sequential manner of arrangement or storage, the array is a linear data structure. So this is the first point which I am trying to make. The second thing is this homogeneous elements. So what does it mean when I just say that the array is can store homogeneous elements? So there are two classes of elements. The first one is homogeneous and second is heterogeneous. You might be knowing, and homogeneous is nothing but this the other term for this similar element. So arrays are basically used to store similar elements only. Okay. So let me give an example so that I could explain this point. So yeah, so let's take one array, integer array. Here are 5. Okay, and one character array. Okay, here only AR and 4. Okay, let's say. So if you know it, then it's fine. It's an array declaration in C or C++. But even if you don't know, so it is like specifying what kind of array elements would be there, and what would be the size of the array, and what is the array name. We have a separate section of this declaration, and I will be talking about this declaration part. But till now, just see that this is not rocket science. This is pretty much simple, that you are just specifying the type of elements which are there in the which are going to be there in the array. This is the array name, and this is the size of the array. Okay, and again, this is the character is the array data type. This is the AR. This AR is the array name and of the character array, and this is the element. Okay, so if I just draw the structure, it would be something like this. There would be 5 chunks of memories, and here there would be 4 chunks of memories. Okay, after this declaration, this kind of structure would be present in the memory. Okay, so if I want to just store some character, okay, let's suppose I'm trying to store in this integer array. So this is not possible, because we have declared the array to be of integers only. So we can't store the characters, any character. Okay, and again, if I just want to store any integers over here, so this is not possible. Only characters can be inserted. And when I say that I'm not able to insert 1, it is integral 1. It is 1, and it is not this one. Okay, so this one is, you might be aware of this thing, that this one is different than this. Okay, so this is the character one. Okay, and this is based on the ASCII value, and the representation is there, and this one is integral 1. So this integral 1 is storage is not possible in the character array. Okay, so this is the thing. So array is a linear data structure, we have seen. It can only store homogeneous elements, we have seen. Okay, so this is about the array definition. Let me use it. Okay, so we have talked about the array definition. So let me just quickly go to the characteristic of array. Okay. So before moving to this characteristics of array, so actually I just want to know if you have any doubt. I can just scroll the slides to the previous and we could just discuss the doubt. So if you have any doubt at the moment, you can just say it with me. Hello.
Hello, sir.
Yes, yes.
So the for loop, the example you have shown in that
This
for
one.
loop, what is the yeah? So here big O of n, the time complexity for big O is also big O of n, and
Yes.
the time complexity for omega is 0. Correct.
So so basically, see, so you might see that the time complexity of this somewhere it is written in as big O of n, right? And yeah, and the minimum omega cannot be you can say that it is big O of what you are seeing, omega of.
Big O of one, sorry, omega of 1 or 0.
Okay. Okay, so you yeah, so you might see this as the representation, but if you just look at this loop carefully, okay, so you would understand that the more just proper notation for this loop is in terms of theta only. Okay, you might find it this is almost correct, like this is big O of n is almost correct, like you might see that the loop gets executed for n times. Okay, maximum n times it would take. Okay, so I would be just moving from 1 to n. So the maximum times for which I would be maximum number of steps is n. But big O you generally use for the case when there is a chance when the execution would stop in between. Okay, but the theta is mostly used when the exact number of times is there, like exactness is there in counting the number of steps. Okay, so most appropriate notation for the time complexity of this is theta of n only. Okay, hello.
Yeah. Yes.
Yeah, I hope you have understood. So this can be used for this representation, but this is the most
But
appropriate notation.
mostly we are using big O as a notation.
Yeah, big O, yeah, big O,
As
yeah,
compared to other notations.
yeah, big O, yeah, because the reason because we are using this big O is that because we are mostly considered about this worst case complexity. Okay, we are just want to know the worst case time complexity of any algorithm, because for let's suppose I'm just implemented some algorithm A, and I just want to just give it to you, and but you would be bothered about what this algorithm, suppose this is a sorting algorithm, so you would be bothered only about how much this sorting algorithm would be taking in this worst case. Okay, worst case time. So that's why the this and this worst case complexity is only represented in order or omega of something. This big O notation is mostly used for this worst case representation. So that's why big O you would see in most of the cases, because we just want to know that this algorithm is taking how much time to the maximum. Okay, so that we just want to know, and that's why you would see maximum times this big O of n. Okay.
Yeah. Okay.
Okay, any other doubts? So yeah, in case of no other doubts, let me just continue with the lecture. So yeah, so I will just explain you the definition of array. Okay, so we would now be moving to this the characteristic of array. Okay, characteristics of array we would be seeing. So the first characteristic of array is that the array elements must be stored at contiguous memory locations. Okay, so let me just take an example. So consider this to be an array. Okay, so it is an array of 4 elements, and the first one being 5, 6, any number 1, 2. Okay, so consider this to be an array. Okay, and yeah, so one second. Okay, so yeah, so this point tells us that the array elements must be stored at contiguous memory location. Okay, so before execution of any program, so this data structure, if it is written in any program, it must be stored in some at some in RAM at some particular memory location. Okay, so this 5 would be stored, let's suppose the this 5 is stored at location 100. Okay, and let's assume that the size of integer is 2 bytes. Okay, so you might have just heard that this size of integer depends on compiler, and it is 2 bytes or 4 bytes. So but for the moment, you just assume that the size of array is 2 bytes. Okay, so if the address of this 5 is 2 byte, sorry, the address of this 5 is 100, and I've already told you to assume that this 5 is taking 2 byte, the second element 6 should be stored at 102. Okay, and again this would be taking 2 bytes, so this one would be stored at 104, and similarly this would be stored at 106. So this is this characteristic, that array elements must be stored at contiguous memory location. And the problem with this characteristic is that if we just want to store 1,000 elements, and if we do not have these contiguous, if the contiguous memory location are not present, so then we would not be uh, able to store array. Array storage would not be possible. So that's the problem with array. Okay, but nowadays they are the RAMs are pretty much huge. They are in gigabytes, and also there should not be a problem. And this you have seen, that you are just seeing that it is in bytes only. So that should not be a problem. But yeah, this point you need to just remember. Okay, so yeah, and one more note I would just like to make is that yeah, see this element 5. Okay, so when I'm saying that this 5 is present at 100, so what it means? So basically 5, I've already told you that it would be taking 2 bytes. Okay, okay, so the 5 would be stored in bits in the computer. Okay, or in RAM. So the binary of 5 is 101. Okay, so 415, and it should be stored in 2 bytes. Okay, so consider this to be the storage of 5. Okay, so 101 should be there, and consider this is 1 byte. Okay, and there would be just 5 zeros over here, and then 8 zeros over here. Okay, and yeah, so it would be at 100. This would be 101, and this would be 102, because we have just the compiler has just this assumption that the size of integer should be 2 bytes. So 3 bits would be enough, but we are storing 5 in 2 bytes. So but the question arises when I'm just asking you the address of 5. So why are you telling that the address of 5 is 100? Okay, so the thing is, it is being stored from 100 to 102, but the address of 5 is 100 only. Okay, so this is the convention that when I'm asking about the address of any particular element in this array, any particular element of this array, so you would be just telling me the starting address. Okay, so the starting byte is the address of this of any element. Okay, so this you should understand that in the memory it is being stored in this 2 bytes. Okay, it is spanning 2 bytes over 2 bytes, but the address we are just showing by this first starting byte only. Okay, so this is about the first characteristic. Let me move on to second characteristic. Okay, so this second characteristic is that array elements can be assessed. So this is the way I write A, so not get confused. So assessed using a set of indices. Okay, so consider an array again as an example. This is X. Okay, 5, 3, 2, 1, 4. Okay, so just assume the name of this array is ARR. Okay, so this is the array. Okay, and this point what is trying to just tell is that the array elements can be assessed using a set of indices. So indices are basically indices are basically used to just show the position of the relative position of the elements which are stored in the array. Okay, so and the indices would be just start from 0 to up to size -1, size where size the array size. Okay, in most of the programming languages like C, C++, Python, and MATLAB. So most of the programming languages, this would be this way, that the indexing would start from 0. And in some languages like R, you'd be seeing that the indexing is start from 1 only. So if it is explicitly mentioned, it could be explicitly mentioned in the question that the indexing starts from 0 or 1. But if it is not mentioned, you should go with this, that indexing is starting from 0. Okay, so if this is the index of the first element 0, then this it would just go sequentially 1, 2, 3, 4. Okay, so these are the indexes of these array elements. Okay, so yeah, so what we could do, if suppose I want to just assess this element too. Okay, so it can be assessed easily using the index of it. Okay, so we could just simply write ARR in the square bracket. We could just mention the index of it, which is 2 only. Okay, so let me just take some another example. So or you would be confused because both the index and yeah, the element are same. So let me take this one. Okay, one. So if I just write ARR, and in the square bracket if I mention 3, so what it would assess this, it would assess this element. Okay, and if I just print it, I could just print it or perform any action. So if I just print ARR 3, it would print 1. Okay, so this is this second point. So you could just directly use the index of the any element to just assess it. Okay, so this is the second characteristics. So yeah, the next thing I'm just going to teach you is the declaration of array. So it is pretty simple. We have already seen in the previous examples. So yeah, so I'll give you two declarations. Okay, so one is very much general. You'll see in the implementation and questions also of gate. But and second one is you can see in some of the pseudo codes, but you must be aware of these kind of declarations so that you can just solve the questions. Okay, so yeah, let me just quickly tell you the first general declaration, which is int arr and 5. Okay, so this is the declaration in C or C++, and similar kind of syntax would be there in the languages. Okay, so yeah, int, where int is the data type, this ARR is the array name, and this 5 is size of the array. Okay, so if I declare this, so five chunks of memories would be allocated to this array, and the name of the array would be ARR. Okay, so this would be there, and the index we have already seen, the index would be 0 1 2 3 4. Okay, so if I write about the indices would be from 0 to this size minus, if we have this kind of declaration. Okay, so yeah, the other declaration is pretty much similar to the first one only. So it is int arr, and what we do instead of the size of which we provide in over here, so what we do, we generally what we could do is give a range, okay, of indices. So let's say -2 to 3. Okay, so yeah, so this could be one possible declaration which you might see. So this is the data type, this is array name, and this is the range of indices. Okay, so and this is what we could call it, this is the lower bound of the index, and this is the upper bound of the index. Okay, LB stand for the lower bound, and UB yeah, stand for the upper bound. Okay, so if you have to just look at the structure, it would be something like this. So the index would start from -2, -1, 0, 1, 2, and 3. Okay, so yeah, and the other name is AR. Okay, so so this kind of declaration you just find very much few times, but yeah, you must be aware of this. And yeah, so and if you just look at this example, you can see that this both of these lower values and upper values are inclusive. Okay, so I've included this also, -2 and 3 also as the indices. Okay, so and if I just tell you how can I just find out the size of this array, you can just use the formula upper bound minus lower bound plus 1 to just state what is the size of this array. Okay, so let me just quickly do it for this example. So upper bound is 3 minus lower bound is -2. Okay, and plus 1. So this is 3 plus 2 plus 1, that's 6. And if you just count it, that the elements are 1 2 3 4 5 6. Okay, so this formula gives you the count of this the array in this kind of scenario. Okay, okay, so this was the slide. Fair slide. So array is a linear data structure which is a collection of homogeneous elements. Characteristics we have already seen, that the elements should be stored in contiguous memory location. All the elements can be accessed with the help of a set of indices, we have already seen. And yeah, declaration also, this is the data type first, the array name for, then, and then the size. Okay, and the indices are from 0 to size -1. Okay, and this is again this is the second type of declaration where we are providing lower bound and upper bound of the on the set of indices, and this size formula which you could use to determine the size in this kind of scenario. Okay, yeah, so yeah, so let's move to some other basic concepts of array. The first one is base address of array. Okay, so base address of arrays is a very simple concept. It is the starting or the address of the first element, and this first element is of course of the array. Okay, so the address of the first element of the array is termed as the base address. Okay, so yeah, again with the example, this is something like this. So 5 3 4 1. So this first element is 5 over here. So let's suppose it is stored at 100. Again, this would be stored at 102. Based on the first characteristic which we have seen of that the element should be stored at the contiguous memory location. So this would be at 104, again 106. Okay, so base address of this array would be 100, which is the address of the first element. Okay, so this is about base address. The one important note which comes from this base address concept is that let's suppose this is the array name. Okay, in AR. Okay, so yeah, so the note is this is very important note. Okay, and it was like if when we just declare any array. Okay, so the name of the array is defined as the as a constant pointer, and it stores the base address of the array. Okay, so suppose this is the array. Okay, so there would be some declaration for this array beforehand also. Okay, so let's say the declaration is something like this: int arr, and because we are having 4 elements, 4. Okay, so this could be a possible declaration for this array. Okay, over here. So this statements what it this note states is that the when we are just declaring only declaring any array, so this is the array name. So what would happen, the arr, which is the array name, would be just defined as a constant pointer. Okay, so pointer is nothing but a variable which is storing the address of some other variable. Constant pointer is nothing but the pointer whose value cannot be changed. Okay, so arr would be just defined as the constant pointer. Okay, and what it would store the base address of the array. Okay, and the base address of this array, we have already discussed that it is 100. Okay, so this would be done automatically by the compiler, that arr would be declared defined as the constant pointer and 100 would be stored. Okay, so this is a very important note, and some of the gate questions are also asked based on this concept. Okay, yeah, one another thing is this location of AI concept. Okay, so suppose some array is there. Okay, and we just want to let's give the numbers to it, like 5, 3, 2, 1. Okay, suppose these are the numbers, and the index would be 0, 1, 2, 3. And let's suppose yeah, and the let's suppose the address of these are 100 again, 102, 104, 106. Okay, so let's suppose these are the address of these elements. So suppose LOCAI represents the location at which the ith element is present. Okay, so it is basically the elements address. Okay, so AI is, I have already told you, this thing is used to just access any element, the ith element of array A. So let's suppose this is A. So AI would be is how we access the element, and the location of AI would be the address of that particular element. So there's a what you could do, if someone asks about the location, you could just draw the its structure. You could just put in the elements, and without putting in the elements also, you could just write the indexes over on the top of it or bottom of it, and you could just find out what is the address. Okay, so but there is a simple formula which you could just use for this for calculating the location, which is base address. Location of AI can be given as base address plus I into W. So I is nothing but the index from here, and W is nothing but W equals one element size. Okay, so W is nothing but one element size. Okay, so you basically don't need to just remember this formula also. So I can just make you visualize, so that whenever you just solve the question, it would just come automatically to you. So let me just make this array again over here: 5, 3, 2, and 1, and it is 100, 102, 104, and 106, 0, 1, 2, 3. Okay, Let me change the color so that it is visible properly. Okay, so yeah, so let's suppose I want to reach this location A of 3, let's suppose. Okay, so A of 3 is basically this point. Okay, and I just want to reach here. Okay, so how can I reach over here? So we could start from base address. Okay, so and this is the base address. Okay, so we could start at base address, and what we could do is we could just make jumps. Okay, from this position we could just make jumps and to reach this location, and the number of jumps which we have to just make to just reach at this point is I. Okay, and I is nothing but the index of the element also. Here the number of jumps, okay, equals the index. Okay, and there is a reason behind this. Okay, the reason is that the index starts from, index is starting from 0. Okay, so this is the reason why the number of jumps is equal to number of index. But when the index would not start from I've shown you some declaration in which the we could just bound the index to start from some other lower bound. So in that case the formula would be different, but just visualize this, and those formula would be just the special cases of this formula. Okay, so base address is where from which we start. Okay, and I would be the number of steps, okay, which we just number of jumps which we make. And but we just want to just talk in terms of location or the address. We just need to specify in that step how much just address we are skipping also. Okay, so we are not bothered about the index, we are just bothered about the size of this of each element, so that we could just arrive at this location and we could say that okay, so this much address we have just skipped. So that part we could add by multiplying w to this I. Okay, so base address is where we start, I is the number of jumps we make, and w is the size of each element or the width of each jump, so that we could arrive at a particular index. So this way you need to visualize every formula. You don't need to remember any formula in computer science subject. Most of the formula I would say you could visualize like this, so and you don't need to remember the formulas. Okay, so after visualization part is there done, so let me just calculate this also so that the formula gets verified. A3. Okay, so according to formula it is base address plus I into w, where the base address is 100 plus I is 3 from the question itself, and we have assumed that the w or the one element size is 2 because integers are being stored here. So 2 would be there, so 100 plus 6, that's 106. Okay, and you could see that this is 106. So yeah, so this is about location of any array element. Let me okay. So yeah, so we have talked about the base address, which is the address of the first element. We have talked about this node, that the array name would be defined as the constant pointer and it would contain the base address. We have already talked about the location also, the location of the element. The location of A can be calculated by using this equation, base address plus I into W, where I is the element index and W is the size of each element. Okay, yeah. So let me just move to one gate question. Okay, this is a very interesting question. Okay, and yeah, we are just going to solve it. Let me just, yeah, this color is also fine. Okay, yeah. So what this question yeah, was asked in gate 2011, and this like we just want to what print out, we just want to tell that what is the what is the C program just prints. Okay, what is the output of the C program. Okay, so let me just number the statements beforehand so that we could just trace all the statement and could reach any point. Okay, any answer. Okay, so the first statement stage that we need to just if you are just aware of the, some C programming language, then only you would be just able to solve this. But even if you're not aware of this, I would just make efforts so that you could just understand it. Okay, so the first statement just says that we need to have a character array C. Okay, and C would be storing this whole string. Okay, so double quote in C is basically, double quote in C is used to store string. Okay, so yeah, so C would be used this would be initialized with this value gate to turn element. So GATE2011, and there is no backslash 0 over here, but when the string is represented in double quotes, or the character array, at the end of the character array, the backslash 0 would be automatically appended. Okay, so there would be a backslash 0 automatically at the end, even if you are not specifying. This double quote itself means that there is a backslash 0 at the end. Okay, so this is about the first statement. Okay, this is how the array looks like. Okay, now second, so let me just write down the array index also, element index also, 1 0 1 2 3 4 5 6 7 8. Okay, so yeah, C. Okay, so this is the C array. Okay, so the second is this second statement tells us to just to create a character pointer. So yeah, so P is a character pointer. Okay, so because P is a character pointer, it would be just storing the address of a character. Okay, so and we are told to just initialize this with the value of C. Okay, so the value at first we just need to find out what is the value of C, and this comes from the note we have seen previously, that the value of C, as C is the as C is the name of this character array, this C when we declare this array itself, the C would be just storing the base address of this array itself. Okay, so let's assume that it is the base address of it is 100. So after the execution of this first statement itself, so this C would be storing this 100. Okay, because 100 is the base address of it. Okay, and this second statement tells us that C should be the value of C should be the value of P should be initialized with C, so the P should also be storing the value of 100. Okay, now let's go to this third statement, which is just asking us to, this printf is used for this printing anything which is given this in the parenthesis over here. This percentage s is a format specifier, for strings. Okay, format specifier for string. Okay, so yeah, so this percentage is a format specifier for string, and whatever is written over here is meant to be printed, and this should be the output also, because we are just we have to find out what is the output of this C. Okay, okay, so let me just write down the equation. So let me write down over here, P plus P3 minus P1. Okay, so whatever the output of this we need to print. Okay, so P, we already know that the P is having the value 100, and P of P of 3 is basically E. Okay, so P of 3 is E. Okay, the element at the index 3, it's E, minus P of 1. Okay, so P of 1 is A. Okay, so yeah, so the first time you look at this question, and you if you don't have the proper understanding, you just think that this question is wrong, or the because how can we just subtract the values, the alphabets. Okay, so there is no way we can subtract this. So at first time, if you don't have any understanding of it, you just think that whether it is a wrong question, or it is the answer of it would be a compilation error. But this is not like that. So the concept which you need to be aware for solving this question is that the characters are basically stored in the form of ASCII values, okay, in C. Okay, so every character like A, B, C, D, a small a to a small z, everyone every one of these characters would be having some values assigned to it, and that's how they are stored in computers, right? Because computers don't know about this characters. Okay, so the capital A is having the value of ASCII value of 65. Okay, and this is I think this is the having the value of 97, actually. Yeah, so yeah, so this A is having the value of 65 and E is having the value of 69. Okay, so if you remember the ASCII values of these two characters, you could easily just substitute over here, and you can just find out 100 plus 69 minus 65, that's 100, plus 4, and that's 104. Okay, 104. Okay, so yeah, I'll just here I'm assuming that you just remember the ASCII values of this the two characters. But even if you don't remember the ASCII values of these two characters, I'll just explain how could you could answer the the question, even if you don't remember the ASCII value. And this I would just tell you at the end. Let me just solve the problem from this point where you have got the value of this equation to be 104. Okay, so this equation is giving me the value of 104. So 104 is okay. So yeah, so this is giving us the value of 104. So the now the thoughts could be that the elements, the output could be this 104 only. Okay, we might think that because this is there, this is the output of this, the 104 can be the output, or the let me just write down the address of these elements also, so that the question would be clear. So yeah, so one more thing, that the size of any character is 1 byte. Okay, in C. Okay, so this one would be stored at 100. So this one would be at 101, 102, 103, 104, 5, 6, 7, and 8. Okay, so this would be the address of, so this would be 10. Okay, 10 is there before it. Okay, 108. Okay, so the thoughts which could come to mind that after reaching to this point is that 104 could be the answer, or the value at 104, which is 2, could be the answer. So but both of these thoughts are incorrect. Okay, so the question can be solved if you don't know one more interesting point about this percentage is. Okay, so this percentage is what it takes. Okay, it takes basically an address. Okay, and which you have seen that it is taking 104. Okay, so the value of this is 104 only. So it takes the value of an address, and it keeps on printing until it gets \0, or until there is the end of the string. Okay, so what it would do, the percentage s would just take this 2 and print. Okay, again after that 0 is there, so 0, it would print 0, and then 1 and 1. Okay, so 1 and 1, and then it would arrive at \0, but it would not print at that, and it would just complete its execution. So the output of it would be 2011. Okay, so this is the output. Okay, so this is a very interesting question, and you need to have the knowledge of several concepts. And the motto of this of adding these questions is that the questions can be this much complicated, or this much concepts might be, this many number of concepts might be there in gate. So you need to have very good understanding, good grasp of the fundamental good fundamental understanding of all the concepts, so that you could just link the concepts and you could just reach the solution. Even if you just miss the any part, you would not be able to reach the solution. Okay, so I'll just repeat what are the important concepts which are involved. So the first one, the backslash would be appended automatically. The C would be just storing the base address, so that we could just assign its value to P. And then we could just we could just subtract the it is not like we can't subtract the alphabet. We could subtract, and we could just do it with the help of ASCII values. After that, we just reach address, and this address, when given to a percentage s format specifier, it would just keep on printing until backslash 0 is there, and it would not print backslash 0. Okay, so these all concepts need to be just remembered, so that we could just solve this problem. And one more thing I have already told in between, that even if you don't remember, even if you don't remember the value of ASCII value of A is 65, and even if you don't remember the ASCII value of E is 69, you could easily solve this problem. But you must be aware of the fact that this concept, that the ASCII value are sequential in nature. Okay, so whatever the value ASCII value of A capital is there, the B would be one greater than this. Okay, so it would be 66, or yeah, even if you don't remember the exact value, you must be aware of this concept, that the ASCII values are sequential in nature up to capital Z, capital Z, and again for a small z. So this all these values should be sequential in nature. So consider this example, this equation I'm talking about, 100 plus E minus A. So yeah, so consider x a to be the ASCII value of A to be x. Okay, and you know that the ASCII values are sequential in nature, so E would be x plus 4. Okay, so because from A to B, you increment once. Okay, then B to C, then C to D, again D to E. Okay, so four steps you take from A to E to reach the E. So that's why if the ASCII value of A is x, so ASCII value of E would be x plus 4. Okay, so if you just subtract these values, so x would cancel out, and you would get 4. Okay, and 100 plus 4, you would get 104. So this is the value which you get. So even if you don't remember the ASCII values, but it is recommended that you just remember some of the ASCII values, like you just remember the starting at this A ASCII value, capital A, so that this is the starting point, and you could just calculate the value of Z up to Z, because you know that the ASCII values are sequential. Again, you just need to remember this small a, and some of the characters like backslash 0, backslash T, backslash N, because in some of the questions they might just use the ASCII value concept, and they might not just give you the values there, and you might need the ASCII value. So yeah, so this is about one of the gate questions. I find this question very much interesting, and yeah, this is about this question in gate 2011. Okay, so it's already 7:30. I thought that I would be covering two to three more slides, but so do you want me to continue, or what? Actually, I was told that I have to take class of around 1:30. So what do you want? So anyone?
Sir, one doubt.
Yes, yes,
Sir, why you take the ASCII value when it is P of 3 and P of 1?
yes.
Can
Okay.
you explain?
Yes, yes, yes. So see, this was the array, right? GATE2011, right? So this was the index 0 1 2 3 4 5 6 7. Okay, so P of 3 was E. Okay, and P of 1 is A. Okay, so if I'm there to subtract the values, okay, so I'm told to subtract the values of p1 from p3, right? So this equation would be something like, if I just consider this part only, so it would be E minus A. Okay, So you can just perform it. You can write this code fragment in some C compiler, and you could compile and check. So this would just give me a value of 4. Okay. And the reason behind this is the implementation of these characters in the form of ASCII values. That's the basic implementation which is there, that these characters are stored in the form of ASCII values. And because ASCII values are nothing but integers, and we can perform this subtraction operation on integers, so that we could just arrive to this value 4. So that's the point. Okay, so that's the
P
inner implementation. Sorry.
here P of 3, here P of 3 and C of 3 both are E,
No,
because
you have,
C,
it is P of 3 and P of 1.
yeah. So the array is C, correct? So
Yeah,
C
array
of
is 3.
if C of 3, then we'll get E also,
Yes,
and
yes, correct. C of
uh,
3 is E. Okay. Yeah.
so pointer of 3 also it is coming as E, correct?
So this is what you want to tell me, right? C of 3 is E, correct?
E. So
Okay.
its pointer star P means pointer, correct? So pointer of
Yeah,
3 is also
pointer of
E
3
only.
is also 3. E. Yeah, that's correct. Okay.
Yeah.
So yeah, so
Okay.
that's why this P3 is E, and that's why this P1, which is equivalent to C1. Okay. This P3 is equivalent
Okay.
to C1, and that's why this P1 is A. Okay. And
Okay.
then
Okay.
the story is, we can just subtract the alphanumerics, the alphabets, but we can just subtract this ASCII values. They are ASCII values because the inner implementation is using ASCII values only. Okay. So that's the whole concept. I hope you understand.
Yes.
Okay. So any more doubt? Actually, I'm not able to see how many students are there. Let me hide this. Oh, sorry. Actually, one second. This escape is not working. Discard. Okay. Okay. So yeah. So any other doubt? Actually, I can see that there are only 2 students. So yeah. Any other doubts? You can unmute and you can just ask.
No.
Okay. Okay, that's fine. So actually, I was just told that I have to just conclude the class at 7:30. I had just planned to just include some other topics like so the algorithms on array, but as the time has exceeded, so I'll just leave these 2 or 3 slides, and I would just end the class. Okay, at the moment. Okay, so yeah, so that's it. That's it about. So let me just open the slide for this. Okay, one second. Is the slide is this slide visible?
Yes.
Okay, so let me just quickly summarize what we have seen, and because yeah, one second. Actually, I'm pretty much new to this WebEx, so I'm finding some problems. One second. Okay, yeah. Yeah, this one both. So what we have studied today is this time complexity, okay, and this asymptotic notation, Okay, and briefly we would just study about it in more detail, because these are mostly covered in this algorithm subject only, so we would just discuss it more deeply when we just start this algorithms subject. Okay, and then we just switch to arrays, and we just looked at its definition, then we looked at its two characteristics, and then we just looked at it two declarations, two types of declarations. Yeah, then base address concept, then this the base address concept, then this the constant pointer concept, the that the name of the array stores the constant it declared the constant pointer, and it just stores the base address. And then we just looked at this location of AI concept. Okay, that we could just find out this location of any element using some formula which we have discussed already. And then we just did the gate 2011 question. So this is the summary of today's lecture. Okay, in case of any doubt you might ask, or you might, yeah, we would just if in case of no doubt, we would just end the lecture. So I hope that there is no doubt remaining, and I hope that you understand the concepts. Uh, yeah, and you are just comfortable with these concepts. So with that, I would just end the lecture. Have a good day. Thank you for
Thank you,
attending
sir.
this lecture.
Thank you,
Okay,
sir.
okay.
Good night.
Good night.